Welcome, students. In this video, we are going to study section 2.1 on tangent lines and rates of change. Let's start with the following definition of a tangent line. Suppose that x0 is in the domain of function f. The tangent line to the curve y is equal to f of x at point x0, f at x0, is a line with equation y minus f at x0 is equal to m tan multiplied by x minus x0, where m tan is the slope of tangent line at point x0 defined as limit when x is approaching to x0 of f of x minus f at x0 divided by x minus x0, provided limits exist. Let's recall how we derived that definition on our very first lecture by selecting arbitrary point Q that is different from point P. So point P, we are trying to find the slope of tangent line at point P. Then we are going to draw a secant line that is going to pass through points P and Q. And then when we are moving closer and closer point Q along f of x to point P, we can see that our secant line is going to approach to tangent line, meaning that limit when x is approaching to x0 of slope of secant line is equal to the slope of tangent line. And the slope of secant line is defined as tangent of that angle here, which is equal to the ratio of that side length over the ratio of this over this side length. Right, we can also derive the following definition. If we define x minus x0 as h, then we can replace our slope of tangent line in the equation of our tangent line as the following limit when h is approaching to 0 of f of x plus h minus f at x0 divided by h. This is a similar argument, but this time we're replacing x minus x0 by h. Another common notation you might have seen is when we replace h here by delta. So limit when delta is approaching to 0 of f at x0 plus delta minus f at x0 divided by delta. All right, now let's take a look at a couple of position versus time curves. Let's recall that velocity is a vector that contains information about speed of an object and direction where it is moving. So the norm of that velocity vector is equal to speed. In other words, the length of that vector is the speed of your object. Let's assume that we have a car that is moving only in a positive direction with perhaps maybe it's slowing down or speeding up along the way, but it's moving only in the right direction. Then if we take a look at position versus time curve, where in y-axis we have position of our car about origin somewhere here at 0 versus time, we'll get the graph that looks like this. So we can see that it is always increasing, meaning that our car is only moving in the positive direction. Now let's take a look at another case. Let's assume that we have a guy that is throwing a ball, and then a ball is in free fall. So if we take a look at position versus time curves, then the ball is going to first of all, let's define 0 as the ground and 0 as the ground, S0 as the point where our person releases the ball up in the air. And we assume that positive direction is going to be up to the air. Then our graph of position versus time is going to look like this. So we can say that position of a ball is going to increase up to some point. Then due to the gravitational acceleration, it's going to reach its maximal point, and then it's going to fall down. All right, now if we define our s as a function of t, then we can use the following equations for average velocity and instantaneous velocity. So average velocity is the change of position over time lapse between those 2 points. So let's assume that we are looking for average velocity over time interval from t0 to t0 plus h. Then average velocity is equal to f at t0 plus h. Let's recall that f of t is a position where it's a function of position of our point minus f at t0 divided by h. Instantaneous velocity is defined as the slope to our position versus time curve and defined as the limit as the slope of tangent line at that point t0, a limit when h is approaching to 0 of f at t0 plus h minus f at t0 divided by h. Okay. Now we have similar argument. Basically, average velocity is the slope of secant line adjoining those 2 points at t0 and t0 plus h, and instantaneous velocity is instantaneous velocity at point t0 is the slope of tangent line to the curve, to the position versus time curve at point t0. Now let's define what we mean by rate of change of y with respect to x. In case when we are working with a simple linear function y is equal to mx plus b, like in this graph we have here, then one unit increase in x always produces m unit change in y. So if we are moving to the left from our current point by 1 unit in direction of x-axis, then it is going to result in m unit increase in y direction. And similarly, in our case here, if we are decreasing our value of x by 1 unit, then our value of y is going to decrease by minus m. And we define average rate of change of function f of x in interval from x0 to x1 as the following ratio, which is defined again as a slope of secant line. So value of f at point x1 minus f at x0 divided by x1 minus x0. And instantaneous rate of change is similar to instantaneous velocity at a point, is defined as a limit when x is approaching to x0 of f at x1 minus f at x0 divided by x1 minus x0. So this is the slope of tangent line to graph f at point x0. All right, this concludes our section 2.1 on tangent lines and rates of change.